Okay, so this is part 3 of our lecture on sets. Last time we were talking about subsets. And remember, A is a subset of B in case if X is in A, then X is in B. That's what it means. So let A be any set, then I claim we have the following subset comparisons. First, I claim the null set is a subset of any set. So if A is any set, the null set is always a subset. Why is that true? Because if we translate it into this conditional statement, it says what? If X is an element of the null set, then X is an element of A. Well, regardless of what X is, it's never an element of the null set. Therefore, the hypothesis is always false, which makes the conditional statement always true. And if this conditional statement is always true, then sure enough, the null set is a subset of any set. What's another thing that's always true? Every set is a subset of itself. So A is a subset of A. How do we see that? By again translating it into the conditional statement. What does it mean for A to be a subset of A? It means this conditional statement, if X is an element of A, then X is an element of A is always true. Well, no kidding, it's always true. If X is an element of A, certainly it's an element of A. Another property that's always true is A is a subset always of the universal set. Why? Because this conditional statement again is always true. What's that conditional statement? If X is an element of A, the first set, then X is an element of the universal set. Well, if you think about the conclusion, X element of the universal set, since the universal set contains everything, it certainly contains X. Hence, the conclusion is always true, and if you think about it, whenever the conclusion is always true, then the conditional statement is always true. Because the only options would be what? False implies true, which is true, or true implies true, which is also true. Okay, in general, if you want to show two sets are equal, if you want to show the set A is equal to the set B, the way you do that is you show A is a subset of B, and then you turn around and show B is a subset of A. If you show both of those things, then really what you've shown is that you've got exactly the same elements in A as you do in B. Hence, they are the same set. And I'd like to remind you that again, if you were to show A as a subset of B, how would you do that? Well, by showing this conditional statement is always true. How do you do that? By showing it's never false. How do you do that? By supposing the hypothesis is true and then showing the conclusion is necessarily true. So if you ever want to show A is a subset of B, what you do is you suppose X, an arbitrary element of A, and you need to show that X is an element of B. Okay, the next special set I had mentioned almost in section 1, and it's called the power set of A. It's denoted script P of A, script P for power set. And what is it? It's the set of all possible subsets of A. So that is the power set of A, the set of all possible subsets. Let's look at a few examples. Suppose my A is a set 1, 2, 3. What is the power set of A? And that is the set of all subsets. Okay, you recall that the null set is a subset of any sets, so it's in the power set. What other subsets are there? Well, let's name the ones that have cardinality 1. There's the set 1, that's a subset. The set 2, that's a subset. The set 3, that's a subset. Those are all the subsets with cardinality 1, that is, that have just one element. Now let's name all the subsets with cardinality 2. Well, if you think about it, there's a set 1, 2. That's a subset. The set 2, 3. And the set 1, 3. Those are all the subsets of cardinality 2. And let's not forget that the set itself is also a subset. So that's the set 1, 2, 3. So what's the power set of the set 1, 2, 3? It consists of the set of these subsets that we just named. Now notice then the cardinality of this power set is, how many elements do we have in there? 1, 2, 3, 4, 5, 6, 7, 8. So the cardinality of the power set of this set is 8, which, by the way, is 2 cubed. And notice that the cardinality of the original set, 1, 2, 3, of course, is 3. Okay, now let's look at the power set of the set AB. So let's list all the subsets of the set AB. Well, the power set of the set AB again consists of the null set, the set A, the set B, and the set AB. Notice then the cardinality of the power set of the set AB is 4. And 4 is 2 squared. And the cardinality of the set AB is 2. Now let's think about the cardinality of the null set. Or rather, the power set of the null set. What is that? The set of all subsets? Well, so what are the subsets of the null set? And the answer is there's only one. It is the null set. So the cardinality of the power set of the null set is how many elements are in here, how many are in there, 1. And notice I can write 1 as 2 to the 0. These examples lead me to the following conjecture, that the cardinality of the power set is always 2 to the power of the cardinality of the original set. Notice in the above cases, it always worked out. 2 cubed, the original set had 3 things. 2 squared, the original set had 2 things. Even down here, 2 to the 0, and the original set, remember, the cardinality of the null set is in fact 0. All right, we're not going to prove that right now, but that conjecture is in fact true. Here's another property of sets. If I'm trying to figure out what the cardinality of the union of 2 sets is, you might think all I'd have to do is count how many things are in A, that's the cardinality of A, and add the cardinality of B, right? Count how many things are in A and add how many things are in B, and maybe that's the cardinality of the union. The problem with that is you've double counted some things. What have you double counted? And the answer is you've double counted elements that are in both. And so if you have counted them twice, you need to subtract those out once. Now, set theoretically, what are the elements in both? And that is represented by the set A intersect B. So in fact, the cardinality of A union B is the cardinality of A add the cardinality of B, subtract the cardinality of the intersection. Now, if A and B are sets, we call them disjoint in case they have nothing in common. And how can I say they have nothing in common? I can say in case their intersection is the null set. So what does it mean for 2 sets to be disjoint? It means that when they intersect, I get the null set.